RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
So today I want to talk a little bit about some practical things that have happened with the network dynamics, and then talk about how the error correcting code stuff directly addresses that. So if you remember several months ago when we talked about error correcting codes and how that gives us a way to deal with liveness issues.
I was just going to ask if we could revisit just a little bit, just briefly, this stuff about error correcting codes and how it relates to safety. It's been a little while since I've thought about that, and maybe it'd be helpful for everybody else.
I'm going to do that for sure, but I'm going to do it in the context of this particular problem.
Okay, cool.
So first I just want to check in and see if you understand the problem.
The problem with consensus, or what are we talking about?
What we're seeing right now is a problem in network dynamic equilibria. So the issue is that if you have a bunch of validators, all of whom are identical in spec, one validator can pull way ahead of the other validators. So all the other validators are just processing blocks validated or proposed by the initial validator. So we have some validator that receives a deploy from a client and then runs the contract associated with the deploy and then does a replay as a part of the validation of that computation and then forwards the proposal, the block, on to other validators. So at that point, its checking of the block is in its past, and it can go on to do other things. Right. All the other validators have that block to deal with. And so under certain kinds of conditions with respect to network latency and things, that validator, even though they're all equivalent in terms of network bandwidth and storage and compute capacity, that initial validator can race ahead of all the others and be the only one that's proposing blocks in the network. Does that make sense?
Yeah.
Right, and if that's the case, then obviously the network doesn't have very much security, right? You've only got one validator ever doing anything.
Right.
Good, okay, we understand the problem. Mm-hmm. Now the next step is, do you agree that this is a liveness problem?
Yeah.
Okay, good. So then the whole point of the error correcting codes is to address liveness, and in particular, to give a language for addressing liveness. Rather than go all the way back to the full-blown glory of the framework before, I'm going to talk about a constrained version of it, and then slowly widen the scope of the discussion to where we can see why the full-blown version, why this is a subset of the full-blown version. So now I'm going to propose a solution. Okay, so the solution to this comes from the block structure that we use in Casper. So in Casper, we have this idea of justifications. Mm-hmm. Every block that is received by a validator has a pointer to the hashes of blocks, essentially previous blocks that justify this block.
Yeah.
And so a little bit about the history. This idea of using justification pointers goes all the way back to the game semantics proposed by Hyland and Ong for linear logic. And I knew about this, since those days. I was aware of that, the use of justification pointers. And essentially, they use justification pointers as a way to reason about the threadedness of particular computations. And in the 2008 timeframe, I started adapting that idea for network security. I was building a version of what we now have as RSpace, and I wanted the nodes in that network of RSpace nodes to have a means of doing protocol security. And so I introduced the idea of justification pointers. And you can go and look at the Special K GitHub, and you can see the code, the Scala code that gives a fairly abstract, generic style implementation of justification pointers as a part of a network security for a network protocol. So Vlad and I were discussing this, and it hit upon the idea that we could use justifications to go after equivocation, because essentially equivocation is a form of non-single threadedness. So, and out of that grew safety. This is the beginnings of correct by construction. Casper was the justification pointer structure. Now, the idea is to use the justification structure to limit what are good justifications. Imagine that we sort of divide the network from the perspective of a particular validator into player and opponent. So the validator is the player, and all the other validators in aggregation we think of as opponent. They represent the environment. And so now, hopefully that kind of gives some hint as to how this is related to game semantics.
Yeah.
So if you have good alternation in the justification structure, so player goes, opponent goes, player goes, opponent goes, something like that, then the rabbit can't race ahead. Does that make sense?
Yeah.
By opponent going, you mean everyone in the blob of others validates?
Just so we're on the same page, what I'm talking about is the spanning tree of the justification DAG of a particular block, right? And what I mean by good alternation is the root of that tree is the block being proposed, and then the next layer down, is a fringe of justification blocks, and then they have corresponding justifications, which give you a new fringe, right? And what we're saying is that first fringe has to be opponent. It can't be player, right? And as long as you keep that structure going, player, opponent, recursively throughout the spanning tree of the DAG, then everybody's waiting for they're alternating with their environment, right? So the player can't race ahead. And what you can see in the data that we have is that the justification of the rabbit blocks is another rabbit block, right? And the justification of that block is another rabbit block. So rabbits are sort of self-justifying.
What's a rabbit block?
A block proposed by the validator that is racing ahead of the others, which I'm calling a rabbit.
Yeah.
Right. So what you get are these long chains of, the rabbit proposes this block, and the justification for that is this previous block that the rabbit proposed, and so on and so forth, right? And so it's this lack of alternation with the environment that is allowing the rabbit to race ahead.
Yeah, it's like, that validator is not even really paying attention to what is going on in the environment. They're just doing their own thing and
exactly. That is
blocks.
Yep, that is exactly right. And so this alternation property becomes a liveness property.
So when you enforce this alternation for every validator considered as a player, doesn't it become equivalent to not a single validator can go until all of the others have gone?
Very good question. So that leads to the next refinement. So you're rabbiting ahead of me. so that leads to the next refinement. So there are two things you have to worry about. So the first one is the very initial condition, right? So in the initial condition, if you require that the validator's first block that it's ever produced or proposes has to have this justification from the other validators, everybody's stuck.
Yeah, right.
Right. So that's a deadlock condition, and that's directly, this is clearly, liveness and deadlock are closely related, right? So what you can allow for is an initial prefix. The first thing you can do is you say that the genesis block, which is the thing that kicks off everything, is really signed by all the validators, and because it's signed by all the validators, any validator can use that as sort of its initial justification.
Mm-hmm.
You could get off the starting block that way, and then you can allow for an initial prefix, right?
Mm-hmm.
So you have some number of blocks that bottoms out in the Genesis block that are self-justified, but then after that you have to have good alternation. And that gives you enough wiggle room in the network to allow for there to be some decent flow of blocks around the network before you have to start paying attention to your environment.
So you're saying you would have like some kind of upper bound for these non-alternating blocks, and then after that point they have to have this good alternation property?
Correct. That's exactly right. Yes. And then the other refinement is you don't necessarily want it to be all the rest of the validators. You just want a percentage of the environment that's related to your stake.
Right.
We can look at a lot of the dynamics, but just to because we're just having a conversation here. To one simplified version of this is just to say you have to have a third of the stake.
Okay.
And that sort of corresponds to traditional consensus literature.
Mm-hmm.
Like when we were talking about this with Kent the other day, he was saying, well, doesn't this reduce the protocol just to PBFT, practical Byzantine fault tolerance? And it doesn't, because all this is about is the proposal of a block. You don't know that this block won't be orphaned. So it doesn't collapse back down to practical Byzantine fault tolerance. We're just giving a sort of a practical limit, and there are other limits that you could set.
Mm-hmm.
But if you do that, then you get liveness.
Mm.
You get a form of liveness that at least overcomes this particular network equilibrium.
Mm-hmm.
And we sort of done this by common sense reasoning. You can reduce it to a formal proof, but the more important thing is that you see the common sense argument.
Right.
What does it mean to have 1/3 stake in this context?
So when you look at the validators in the justification, each of those validators has a corresponding stake. That's what it means to be a validator. And you want that stake to add the sum of the stake of the validators that are in the justification, that are not the proposing validator, need to sum to 1/3 of the total stake.
Okay.
And you know the total stake because that's in the Genesis block. Knowing the valid set of validators, or the legal set of validators, is critical to the protocol functioning.
Yeah.
And maintaining this condition is what you're referring to as the equilibrium?
No, the equilibrium is just that the validators are communicating without there being live lock or deadlock but the condition gives you good equilibria. You can express this in von Neumann-Nash style games, and you can talk about this literally as Nash equilibria. There's a close relationship here, but I'm not going to sketch that out here in this conversation.
How does validator rotation influence this?
Yes. So essentially what you have to do is, as a part of the protocol, when validator rotation happens, then you have to update the validator set, and that will then potentially change who is allowed to be listed in justifications.
Okay, that makes
Right.
sense. Yeah.
Yeah. So there's lots of kind of interesting recursive things that happen in the protocol, because it's like you don't want validators to censor validators being rotated and so on. But that's a separate discussion from the one we're having.
Mm-hmm.
Okay, we've sort of talked about some relaxation on the good alternation property.
Mm-hmm.
Right, so we allowed for an initial prefix, and we're looking at a percentage of the stake. The full liveness error correcting code thing can be transformed into a specification of weighted grammars on the justification DAG. When we talked last time, we sort of introduced the space calculus.
Yeah.
Which allowed us to do this programmable liveness conditions.
Mm-hmm.
And the liveness conditions essentially looked like a context into which you deployed your process, and then we made it programmable by making context first class, and you can ship them around and that sort of thing. And that's what gave us the space calculus. The basic idea of encoding the context can be transformed in a step-by-step manner into a constraints on the justification DAG. Because what they do is they tell you what are allowable communications, and the view of the allowable communications is represented in the justification DAG. This particular block is justified by these communications that I have seen. And those communications are justified by these communications that other validators have seen. So this is how you practically realize this error correcting code idea in the Casper protocol. Let's talk about how all the pieces fit together, just so that, because there are a lot of moving parts here, and I just want to make sure that everyone understands the moving parts. A few months ago, I sketched out how you can turn the error correcting code idea of liveness into a context-based encoding, and then make that programmable, which gives you a language for talking about liveness constraints. But what I didn't say was how to relate that directly to the implementation in Casper. When we didn't relate it to observed liveness issues in the running protocol. Right, so we just sort of said, here's a nice theory. It has some lovely properties, like it's amenable to bisimulation and therefore, constrainable by types and yada yada yada. Right, lots of nice properties of this thing, but we didn't connect those good properties to a running implementation. Now we have the running implementation, and it is facing real liveness issues that are observed by our SREs and in testnet too. So you can see the proposed times of validators lengthening under certain network conditions. And it turns out that if you run a particular constrained network conditions, which are natural when you're just sort of beginning to test the thing, you don't observe them. It's only under certain kinds of load that they start to take hold. It's a subtle issue in network equilibria.
So what's causing the increase in the proposed times?
It's because the rabbiting validator is able to get an edge up on all the other validators.
Okay.
Yep.
Yeah.
Yep.
So this is undesirable behavior.
It's undesirable behavior. That's exactly right. And we want to eliminate it, and we're able to demonstrate that it's clearly a liveness issue, and we can now give a crisp answer how to address the liveness issue in terms of just the code of Casper. But then we can connect the dots and show that solution is part of a larger solution which is contained within our theory of programmable liveness.
Cool.
Awesome, yes?
Yeah, that's pretty cool.
To me, this is sort of how this kind of software has to be built.
Yeah.
And in particular, the methodology that we used here was to go slow and make sure that we observed real issues and then applied just enough of the theory to resolve the issue. And sort of connect the dots in that way. There are two approaches to this. You start from a place of correctness, and you only do transformations that preserve correctness. And so that's what we're doing. But the other side of that is there are some aspects of correctness that ignore or are insensitive to emergent issues like network equilibria.
Yeah,
and so
performance.
Performance, exactly, those kinds of things. And so you have to make sure that you're willing to kind of take both sides, right? You're only doing correct transformations of code, but you're also looking out for these emergent phenomena and making sure that your theory is capable of handling those, and then applying the theory to resolve those kinds of things in a disciplined manner. And that's sort of what we have done here. And the nice thing is that it results in a fix that takes, it's just a couple of lines of code to ensure this property, and can be rolled out in a week. But we know that it's grounded in an argument for correctness, and we know that it's connected to a theory that we can reason about algebraically, equationally. Right. That's the raison d'etre for CBC Casper. That's why we do this.
Yeah, cool. So you said there is a working implementation of this currently?
Yeah. So it's we found the problem. This Monday we had a good long talk to make sure that we were in agreement about the parameter, because you notice that the solution is parametric, so we wanted agreement on the parameters. And now it's ticketed, and the work has been assigned to one of the engineers and is being implemented as we speak.
Cool.
Yeah.
Sorry, but it's not quite clear in my head how this is working. Could we possibly walk through a simple example of it in practice?
Sure. Let's start with the problem. The problem is that the dupe contract is proposed, and the dupe has a lot of recursion in it. So it does many layers of recursion. So the client deploys this to the validator. The validator then runs the contract and then replays the contract, and then proposes the block with that to the rest of the network. The validator Alice has done that much work. And now all the replay is behind Alice. So Alice is now free to respond to other client requests. So if you have a client requesting, say, on the order of every 5 seconds, the other validators, if they have taken up Alice's work, then they're stuck on that work, unable to give much attention to any client requests. Is that making sense?
Yeah.
Okay, great. And so Alice can get further and further ahead. But the only reason that she can get further and further ahead is because the blocks that Alice is using as justifications for the blocks she is proposing are blocks that Alice has proposed.
Yeah, right.
If we insist that, one, the Genesis block is, since it's signed by all validators, constitutes the totality of the stake of all the validators, then that can be used as a justification for any initial block proposed by a validator. The other thing that we do is we insist on a condition that any block that is proposed, it's the blocks that justify it must contain at least 1/3 of the stake from other validators. We don't care which ones they are. It just can't be Alice or whoever is proposing the block.
Are these requirements like being encoded in the contextually in the space-time calculus or something? It wasn't clear to me how that aspect of it.
So that so how that connects to, so that becomes a context. What you would do is you would turn that into a context, which is enforcing that kind of alternation.
Okay.
The context would sit there and wait and collect blocks. So that's how you connect the two. And then once you have this alternation property, then Alice is forced to wait. She can't rabbit ahead of the other validators because she can't be so self-justified.
Yeah.
Does that help?
Yeah.
Cool. Any thoughts, questions, comments about anything we talked about so far?
So it's pretty obvious from looking at the justifications which validators actually proposed the blocks that are being used in the justification, right?
Mm-hmm. Yeah. So you get this recursive structure, right?
Okay. So this is just like a protocol enforcement of kind of a general rule of thumb of like, don't believe somebody who is only using their own, work to justify their future work. You want to, look at someone who's taken a little more holistic view of things. But
yes.
I guess which is good. I mean, you do want protocol enforcement of that and not just have a rule of thumb to follow, I guess.
That's exactly right. So the more general thing is that if you think of the spanning tree of the justification DAG as like a term in some abstract syntax, then what we're saying is that these liveness constraints correspond to certain kind of context-free grammars that are weighted, right? It's not just a plain grammar because you were now taking into account the stake weights. And these context-free grammars can also be turned into the kind of Hamming distance-based balls that are discussed in the error correcting code papers that I referred to a few months ago.
Okay.
So it's basically, you know, what's reachable by the grammar can be turned into what's reachable by these Hamming distance gadgets. That's the connection there.
Yeah.
Is each block a term in the grammar, or is the whole DAG a term in the grammar?
The grammar is an outside spec that is saying, when you propose a block, if it isn't accepted by this grammar, it's not valid. It's a rule. It's a constraint. And so one of the things that we discussed on Monday was, what is the in-protocol enforcement about this good shape? Because if you just have the validators implement this logic, but you don't actually punish people who are disobeying the logic, or punish validators for disobeying the logic, at least in some form, then they can still cause disequilibria in the network. So
anytime you're trying to impose some kind of conditions on a certain kind of DAG in the chain, there's like a corresponding grammar, and then there's also going to be some corresponding kind of like context in the calculus?
That's exactly right. So liveness conditions correspond to grammars, and those grammars can be implemented by contexts. So there's a recursion property, which is that every justification DAG is homomorphic to the total blockchain DAG, but they're not the same. A justification DAG is not going to be the same as the blockchain DAG.
Why are they homomorphic?
Because at the end of the day, you're looking at some piece. The block that you've got is not the entire DAG; it's a piece of the DAG. So that's how all the pieces fit together. So let me just finish the point about punishing. So the simplest form of punishment is social ostracism. When you send me an ill-formed block that doesn't match the grammar, I drop it on the floor. If your dog is misbehaving, you ignore it, and dogs typically don't like to be ignored, so they start behaving. It's that kind of the behavior modification. You can go a little further, right? Because even then, it can still be a little bit annoying to have the dog keep jumping up on you. You're ignoring the dog, it's jumping, you're ignoring the dog, it's jumping, and then eventually the dog sort of figures out that as long as it's jumping up on you, you're going to ignore it. And so it modifies its behavior. But during that time, you've used up some communication bandwidth. You could consider additional behavior modification. So in the case of our protocol, that could correspond to slashing. So if they're sending an invalid block, you can slash. The trick is to disambiguate whether you want to do what we call slashing to the bone, where the entire stake is eradicated, or you do partial slashing. And in this case,
slashes.
Yeah, that's right. death by 1,000 cuts. That's right. Yeah. In this particular case, I have a hunch that we should use this kind of approach to deal with network partition and rejoining. So you could modify the condition so that if the validator could provably show, and this part is a little mysterious and tricky for me, but if they could show, look, I've only been able to see messages from these validators in the last little while, and so I'm still respecting the rule, but my total stake is of a reduced pool of validators. Then you could do partial slashing in case that they're lying, and then when the network gets rejoined, they get the other messages, and the partial slashing can be given back to them. So while they're in this sort of endangered, the network is partitioned, they're still making progress, and they're not knocked out of the game. And then if it turns out that everything was verifiably the case, then the partial slashing is returned to them. So this is a much more subtle protocol, and there's lots of edge conditions that have to be checked. But the idea is to use it to deal with network partitioning and then rejoining and reconciliation.
Yeah. Do we have a way to represent an agent's history of observation?
It's a little tricky, right? Because they could lie. They can lie about it. There's some things that we would have to enforce there. That's why you want to do a partial slash, because if there is some lying and someone can later prove that they're lying, then the partial slash remains. Otherwise, if there's no evidence of lying, then they could be made whole again.
Right.
Yeah.
There's no way to make their past communications just transparent to the network.
It's not about their communications. It's about what was sent to them.
Yeah.
You can't prove that they got it. Well, there might be ways to prove it, but that's a trickier thing. And I one step at a time.
Yeah. Right.
Anyway, this is what makes me excited about RChain and these kinds of things. I think these are lovely problems. They're beautiful problems. They're clearly related to not just computer communication, but other kinds of agency. And we have a really powerful theory that answers the questions and directly solves these network equilibria problems. And the arguments, they're common sense arguments. It's the kind of thing that you could walk into a high school and do some basic setup of the thing and expect bright high school kids to get it.
Yeah, this is really nice.